And here we go. All right, so I'm very happy to be here today, getting to talk to this crowd about my PhD work. And so the work I've done falls under the somewhat vague heading of computational and experimental studies in selective organocatalysis. And as is customary, before I get into the meat of the work, I want to spend just a few slides doing my best to explain what this is all about to the non-chemists in the room, which for once there actually are at one of these talks. So the first point I want to make to non-chemists is just that organic synthesis is important. And specifically, the ability to intentionally create molecules with a given structure is of immense value to humankind. And this is just a sort of smattering of areas in which this is useful. So in cosmetics, the ability to create given fragrances or other sort of molecular components of shampoos and beauty products is a terrifically valuable and important industry. So this is methyl dihydrojasminate, which is a synthetically produced fragrance, smells like jasmine. Pharmaceuticals are obviously a huge one. So L-DOPA is a treatment for Parkinson's disease that we'll talk about a little bit more in a sec. Plastics are synthetic organic molecules, dyes and films. So if you want to call it that's not easily found in nature, such as purple, we're reliant on synthetic chemistry to furnish us with these. And then so renewable energy, this is a super broad topic, extends far beyond the reaches of organic chemistry, but organic molecules are nevertheless important to the undertaking of renewable energy. Then agrochemicals. So part of the so-called green revolution in the mid-20th century is the widespread use of designer pesticides and antifungal agents, which permit us to grow food more cheaply and more effectively to feed the world. And so these are all just areas, I've put very large monetary figures here just to convey the vague size of these industries. The only point I want to make here is just that it's important for us to make molecules. Nevertheless, making molecules is very hard. And non-chemists might not appreciate this intrinsically because making regular objects is by comparison very easy. And I want to illustrate this just with sort of a toy thought experiment. Given that this is Cambridge, I didn't want to overestimate the physical skills of the audience, so I've chosen an ideal lamp. And essentially, let's say we have this lamp where we have a base, we have a little switch here, and we have two different sockets in which we can insert a lampshade. And the first thing to point out is that we can put a lampshade on the left here, on the right here, and we get two different non-equivalent products. So you can get what I'm terming an R lamp here or an S lamp over here. And let's say that we desire one of these products, arbitrarily the R lamp, because we're right-handed. On human scale, this is very easy. We can simply take one piece in one hand, take another piece in another hand, and put them together. But on the molecular scale, this is much more difficult for sort of obvious reasons. So molecules are very small. Bond is on the order of 10 to the negative 10th meters. And chemical reactions happen very quickly. So on the order of 10 to the minus 13 seconds. So we can't directly control these processes. And even if we could, making molecules one at a time is no way to go. We need too many of them. And so essentially all chemical synthesis proceeds through unselective application of energy, which can be thought of as essentially taking the components and shaking them together very hard, either by applying heat or by shining light or electricity. Through this unselective application of energy, I think it's relatively easy to understand that you're going to get a completely statistical mixture of products, so 50-50. There's no way to control which product we're going to get. And so the challenge that presents us as people designing to synthesize molecules selectively is how do we control this even when we can't selectively apply energy? And I just want to briefly introduce a few terminology before I resolve this problem. And so the property that these two different lamps have is chirality, which is the property that these objects cannot be superimposed on their mirror images. And so a simple chiral object is your hands. So you have a right hand and you have a left hand. And these are mirrored, but they cannot be superimposed. So they're different objects and they interact differently. So you can put your right hand in a right-handed glove, but you cannot put your left hand easily in a right-handed glove. And so we call these two different objects enantiomers. They're enantiomers of each other. And what we desire is an enantioselective synthesis. So a synthesis that furnishes predominantly one enantiomer. We score how enantioselective our synthesis is typically through enantiomeric excess, or EE, which we define as the percent major minus percent minor. So if we were to obtain 95% R and 5% S, then this would be said to give product in 90% EE. And that's typically considered good enough. That from there, we can typically upgrade things, and that's sufficient. And finally, we also use this term racemic, which is a synonym for 0% EE that chemists use. And just one more slide on terminology. So we don't usually think about this when we're building regular objects, but we can think of plotting this all on a potential energy surface, where we take sort of a starting material and we have a product which is ideally more stable than the starting material so that the reaction progresses in the forwards direction. And then there's some sort of highest energy point connecting these two, and that we have to think about getting over that point. So doing the reaction is like climbing up a hill, and the higher the transition state, this higher energy point, the slower the reaction will be. And so to promote reactions, we often use a catalyst, which is a species which lowers the barrier to a reaction without itself being consumed. So it's like a little machine that makes this reaction easier to do. That's a pretty good way to think about a catalyst for the purposes of this talk. And so now, putting these concepts together, how do we get selectivity when we only have unselective application of energy? What we do is we add a catalyst which selectively stabilizes one transition state to form, for instance, here the R product and not the S transition state, thereby speeding formation of one product over another. And we can think about this. So here I've drawn the catalyst just as sort of a gray blob, which perfectly fits the R transition state, but does not in fact fit the S transition state. So it's just the wrong shape. It's like the wrong glove. And so we can accelerate one over the other and thus selectively form one product. Going back to this idea of a potential energy surface, here we have the precursor in the middle, and you can see that going to either the R or the S product has the same barrier and thus will proceed at the same rate. And when we add an asymmetric catalyst, we lower one barrier more than the other, and thus we're able to get one product favored over the other. Now, this is a pretty good visualization because this makes 2 points clear. Our catalyst must be both reactive, so it must lower the barrier relative to the background uncatalyzed process, and it must be selective, so there must be a big difference between these two energies. And so these are the two qualities we look for in an asymmetric catalyst. Unfortunately, there's several challenging facts here. So one, we don't always know what the transition state is. As I mentioned, molecules are very small and they react very quickly, so we can't exactly watch them. We might not know how to stabilize it, even if we think we know what the transition state is. So we might not know which interactions to engineer. And even if we know what the transition state is and what interactions we want to engineer, we might not be able to make it. Like we need a catalyst that is itself a molecule, and it might be challenging to synthesize or otherwise just impractical. So these are the challenges in asymmetric catalysis. And this is roughly what I'm going to spend the rest of the talk addressing. So I want to tell two stories today. One is about screening for generality with SFCMS. And this is essentially about discovery, thinking about how we discover catalysts and trying to improve that process to find better catalysts. And then the second story is about once we have highly selective reactions, figuring out why they're highly selective and trying to learn things from them that we can deepen our understanding of chemistry with. So I'll hop right into it. Previously, I presented L-DOPA as an example of an important molecule. And L-DOPA is actually one of the first molecules to be made using asymmetric catalysis. So you take this planar starting material, which is achiral, and you add hydrogen across this double bond using this rhodium catalyst to furnish a protected L-DOPA with very good enantioselectivity. And this is an instance where we only care that the reaction works on one product because the product itself is of such surpassing value that we don't need it to work on anything else. We know we want L-DOPA. But more commonly, we desire reactions that work on whole classes of compounds. So there's about 3 million commercially available molecules that you can get on sort of synthetic scales. And so we don't want to have to develop 3 million separate catalysts or even more for different transformations. We sort of want tools that work on a wide variety of things. And this is what we call asymmetric methods. So this is one of the first truly practical asymmetric methods, the sharpless epoxidation, where you take an allylic alcohol and convert it into an epoxide. And what's nice about this is that virtually any molecule that has this functionality can be converted into the corresponding epoxide with excellent selectivity. So this means that no matter what it is, if you have this structure, you know that you can make an epoxide out of it with good selectivity. And so this allows you to engineer it into a route with high confidence. And what's more, there's actually a market for these things. So you can, in this case, this catalyst isn't too tough to make, but if there's a challenging catalyst, you can make it and sell it to other people. Not to make money, but to enable them to actually use it in their research. So people in medicinal chemistry can use this tool. So there's actually a whole ecosystem of these tools that's developed. And so when we think about when we want to make a good catalyst for a method, we add this third property that we want generality. We want it to work for a lot of different substrates. Because a catalyst that only works for randomly or sort of unpredictably is not very useful. It's very frustrating for the end user. And this is essentially what Sharpless said in his 2001 Nobel lecture. With respect to chemical reactions, useful implies wide scope, simplicity to run, and an essential transformation of readily available starting materials. So this wide scope is essentially the idea of generality. And furthermore, generality is one of the key advantages that small molecule catalysts have over enzymes. So this is just one example. There's plenty of examples like this. I've chosen this one. So this is the hydrogenation of a cyclic ketamine. And while enzymes can do this reaction very well for specific substrates, so this is, I think, one of the best known imine reductases out there as of a few years ago. So for instance, this sort of methylketamine can be reduced with very high selectivity, but as you change the substrate, it no longer fits well into the enzyme's pocket, and you lose selectivity very quickly. In contrast, this titanium catalyst has very high generality. So beyond just the 3 substrates shown here, it works for a super wide variety of compounds, and so is a very broadly useful method. And so most methods aspire to generality, yet few achieve it. So as a case study, I want to focus in for the duration of this part of the talk on the Pictet-Spengler reaction. This is a condensation of a tryptamine and an aldehyde to form this tetrahydrobeta-carboline. This is a sort of specific tricyclic scaffold, and yet one that proves to be very useful in a variety of biological applications. So both sort of natural products like this, and then a variety of synthetic compounds investigated by various pharmaceutical companies bear this structure. And in 2011, it was written that although the synthetic power of the Pictet-Spengler reaction has been realized for many decades, expanded application has clearly been restricted by the lack of asymmetric methods. Essentially, this review is saying that it'd be really great if we had asymmetric variants of this reaction so that we could use it more broadly to synthesize these desirable compounds selectively. And so this is, for people who develop methods, this is about as good as it gets, right? People clearly want this, and we can meet this need with our chemistry and our skill set. And indeed, both before and after this publication, there's a vast variety of catalytic enantioselective Pictet-Spengler reactions that were reported. Here's just a few, there's more. And yet, when people actually try to use these reactions in a productive sense, so this is a paper which was after this 7-bromotripargine, intentionally, because they wanted to study it for something else, they were neuroscientists, they tried to use the methods and they found that they failed, that they were unable to make the products via this route, despite the fact that there's published methods reporting to do this chemistry. And we can think about why this is sort of by using a 2D plot. So on the y-axis, I want to imagine different substrates. So this is sort of substrate space, all the substrates we want to use for this reaction. And on the x-axis, we have different reaction conditions / catalysts. So these are the parameters that we're tuning to try to get the best method. And conventionally, the way that this works is that we take one substrate, what we call the model substrate, and we screen sort of a bunch of different catalysts against it. We say, all right, I'm going to find a catalyst for this reaction. Let me screen a whole bunch of different catalysts. And we sort of look and we can see, oh, there's like some catalysts in this region are good, some in this region are good. And we sort of take the best one and we say, all right, I found the best catalyst. Now let's see how it does on other substrates. And we do what's called the substrate scope. And what we typically find is that this is not super good. So it's often good in the region of the model substrate, and sometimes it's good for other substrates, but often it tails off as you sort of lose similarity to the training set. And what we don't know when we do this process is what the overall landscape looks like. So we have sort of no idea what the whole surface is. We're just looking at tiny little slices. And so when we think about how to make this process better, if we want to actually intentionally find the best method here, that's the best overall and not just best for our model substrate. The sort of obvious solution is that we need to look at more data points so that if we take multiple slices of this sort of 2D plot, then we can more accurately reconstruct the underlying potential energy surface. Or it's not a potential energy surface, sorry, the underlying response surface, and figure out what the best catalyst actually is. And so this is an old idea, first proposed actually in the year which I was born by Henri Caugan. But this isn't really practiced much. So there's a smattering of publications trying this in the early 2000s, and people dust it off from time to time. But the reality is that it's just really practically difficult to screen a whole bunch of different substrates because it means a lot more work for the chemist. And our sort of thinking was that this is dominated by the cost of chiral analysis. So it's not very easy to measure the enantioselectivity of reactions in general. So conventionally, we do this via HPLC on single samples. We use UV detection. So we essentially detect how much things absorb UV. And this is tricky because we want fully separated peaks like this, not overlapped peaks like this. So it requires substrate-specific method optimization. And because we're using UV detection, it's very sensitive to impurities. So we need to purify each sample before analysis. So this means essentially that for every data point, you need to get the sample pure, which is laborious, and then you optimize a method for each substrate. and then you run it each individually. And so this really limits how much data we can acquire. It means that trying to study 10 substrates instead of 1 requires 10 times as much time. So what we proposed, the idea that we came up with was to use pooled SFC-MS. And so the idea was that we'd take a bunch of different substrates. Instead of analyzing them one at a time, we would dump them together and analyze them in bulk. Now, not using UV to detect, but using the specific charge to mass response in a mass spectrometer to analyze all the compounds at once. And so this is nice because we can think of the mass spec portion as purifying the molecules. So we only see something with a given mass. So you don't need to physically purify it because we're already purifying it via mass spec. This is now 2D chromatography. So you can resolve all these different peaks at once, even when they're pooled together. And since we don't need a flat UV baseline, we can also use more substrate agnostic gradient methods where we change the polarity of the solvent mixture and we get better separation power that way. And we can do it without using pure material because again, we're using mass spec just to pull out the components we care about. So this works on crude reaction mixtures. So our hypothesis was that we could develop this method and that this would be ideally suited to what we call screening for generality. So using multiple substrate screens to identify more general catalysts. And so this required a few different things. So when we're not optimizing the method very carefully to each substrate, we're going to have to deal with somewhat overlapped peaks. And so we had to do a lot of software development to get some computational peak deconvolution software so that we can accurately get EEs even when the peaks bump into each other. And what we found was we get a root mean squared error of about 5% for pooled samples. So our single sample error is lower than that. So that's a few times higher than conventional HPLC errors, which are on the order of 1 to 2%, but still good enough for primary screening, if not for final reporting. And then we actually tested what happens when we dump a bunch of different compounds together. And this is actually what the raw data looks like. So this is the mass, again, on the y-axis. This is retention time on the x-axis. And you can see that essentially every time we have a blip and another blip, so these two different dots on the same horizontal line, that those are two enantiomers that we've separated on the chiral stationary phase. As you can see, I believe that there's around 20 compounds in this mixture, and that we're able to really nicely resolve many of them. In some cases, we don't get full separation here, but we're still able to pick that apart via peak deconvolution. And we tested this on a wide variety of chemical structures, so a bunch of different analytes, not just one class of compounds, and also on a few different instruments to make sure that this was actually general and not a quirk. And we also made a web app out of this just to make it easy, so we don't have to muck around in code every time we want to run an analysis. We could, analyze hundreds of data points a day using this peak deconvolution strategy. And so now that we had this sort of analytical method in hand, what we were excited about doing was actually applying it to try to find a better Pictet-Spengler catalyst. And so to choose a good set of model substrates to screen on, we generated a big set of potential products in silico, used molecular fingerprints to generate embeddings, and then did UMAP for dimensionality reduction to sort of create a rough map of chemical space. And so this is shown here. And so the gray peaks are the gray dots are essentially all of the different compounds in our virtual product space. And then the blue dots, what you can see are all of the compounds that have been reported before. So this is every reported asymmetric Pictet-Spengler product in the literature. And what you can see is sort of most of the reported Pictet-Spengler products cluster in certain areas. So there's these sort of vast swaths where there's not very many blue dots and there's a lot of gray dots in what we consider interesting chemical space. And so using a variety of methods, including some k-means clustering, we're able to choose a set of red dots here, which we feel better covers chemical space and also are commercially available and reactive. And we chose these as our screening set. And we figured that if we found a catalyst that worked on all these substrates, it was likely that it would work for most of the chemical space pictured here, much better than just choosing a single point to screen off of. And so you can see here that we're varying both different heterocycles, electronics on the aldehyde component, some aliphatic aldehydes, and then also the nucleophilicity of the indole ring, which is in general underexplored with state-of-the-art methods. And so with this, we essentially took every previously reported Bronsted acid catalyst that we could find. So some of these are hydrogen bond donors, which are cooperative with benzoic acid. And we screened them against all of our compounds using our screening for our SFC-MS method to make this easy. And what we got was this big grid of data. And so you can see, first of all, that there's substrates here. There's whole regions of substrates for which no highly selective solution exists under sort of state-of-the-art conditions. So for instance, for substrate 12, the best result is 36% EE, and the median result is a lot lower than that. And in contrast, some of the easy substrates here, like 23, so this is sort of the canonical substrate here, so benzaldehyde plus tryptamine, turns out to be a pretty easy substrate. So a lot of catalysts do relatively well here. So this sort of starts to explain why people often struggle to get their reactions to work, even when they seem so good in the literature. So going further, we wanted to sort of try to figure out what the best catalyst was. So we developed this generality function based on the L2 norm. So this essentially is the root mean squared of 1 minus EE. And so this essentially scores how general a given catalyst is. There's other potential definitions. I'm happy to discuss this more in Q&A, but we think that this is pretty reasonable. And what we can see with this generality metric is that the best catalyst, which also visually looks like one of the best catalysts, is catalyst 12. So the spinal phosphoric acid over here. And so we sort of moved forward with this and a few other catalysts. So we did a little solvent screen and found that we got slightly better results in 2-methyl-THF. And then did a big screen of different chirophosphoric acids. And we found that, in some cases, although other catalysts were better for certain substrates, the catalyst 12 bearing the 1 natural group remained the best. But so more than the actual result, I think that this slide really nicely illustrates sort of the central point of this part of the talk, which is that, so in 10 of the 14 cases shown here, the overall most general catalyst is not best for that specific substrate. So there's only 4 substrates in which catalyst 12 is the best catalyst. And what this shows is that in almost every case, when you just take a single substrate, you're not going to get a result that's representative of the results for all of substrate space. So in a particularly extreme example, if we were to only look at substrate 11, we might believe that this catalyst was the best, and we would be sorely disappointed when we looked at its results for other substrates. That's sort of this Tadol phosphoric acid here. And so this really illustrates why looking at multiple substrates is so important, because you find things that you wouldn't have otherwise found. And so sort of some adversarial controls here. This was all done in pseudo high throughput format. So we wanted to make sure that it translated well to more conventional benchtop scale. And indeed, we found that when we ran things sort of more conventionally in vials with molecular sieves, that we actually saw a boost in almost every case. So our results were now substantially above 90% in a lot of cases, which was encouraging. So the results weren't a fluke of the high throughput format. In fact, the high throughput format was suboptimal. And then also, we were a little concerned about whether we were just finding something that miraculously only worked for the 14 substrates in the training set, but still didn't work for unseen substrates. So we've sort of chosen a catalyst that works well for these ones we picked, but it might not generalize well outside the training set. And so we picked these 3 other compounds, which we discarded for somewhat trivial reasons. And we compared sort of our optimal conditions to the other next best catalysts. And we found that indeed the best catalyst on our 14 compound set was also best for these. And indeed it was quite good, giving us confidence that sort of we had actually some degree of generality present, that we were actually learning something about Pictet-Spengler space as a whole, and not just about the 14 specific compounds that we picked. So we feel that this is a pretty exciting direction, that we're able to find results that are essentially better than state of the art with no new chemical matter. Simply by rescreening in a slightly more sophisticated way, we're able to find better, more general catalysts. And so we think that there's a lot more out there to be discovered in asymmetric catalysis, even just in the space of commercially available catalysts. And that's very exciting and encouraging to me. So I want to shift gears a little bit and now talk about some mechanistic work studying co-catalysis with strong Bronsted acids. And sort of to introduce this, I just want to talk about Bronsted acid catalysis generally. So a Bronsted acid to non-chemists is just an acid. It's a proton donor. It's the normal form of acid that we're used to encountering. And these are very good catalysts for a lot of reactions. So they can undergo proton transfer to a substrate shown in red to form this ion pair here. This protonated substrate is reactive and so can undergo some transformation that a neutral substrate cannot. And then the product releases a proton to generate the acid catalyst. This is how a lot of chemistry gets done. When we think about rendering this enantioselective, we can imagine making the acid itself chiral. And then there's some chiral information in this sort of ion paired complex, assuming we're in a nonpolar enough solvent. And then this sort of chiral acid can make this transformation enantioselective. This was first done in 2004. So some high profile work by Akiyama and Terada using chirophosphoric acids, like the ones I just presented on, for activation of immunes towards nucleophilic attack. And this has become a huge field. So there's thousands of papers on this. It's very successful, but it struggles in one key way, which is that phosphoric acids are not very acidic. So they're great at imine activation, but they're not so good for activation of less basic substrates. So there have been various proposals to sort of lower the pKa and make them more acidic. So Yamamoto has these sort of triflumids. And then recently, Ben List has had a lot of success with these IDPI catalysts. But something that our group has thought about for a while is that we're asking one molecule to essentially do two things, to both be the carrier of chiral information and to also be very, very strongly acidic. And sort of an alternate strategy we can imagine is using an achiral acid that we already know possesses the requisite acidity, something like a strong mineral acid like HCl or HBr. That's what we would do to run these reactions if we didn't need to do them enantioselectively. And we could intercept the ion pair we form with a chiral anion binding catalyst, like a dual hydrogen bond donor. And this can sort of make this ion pair chiral and promote enantioselectivity in the resultant transformation. And so we're essentially now we have two pieces, one that's acidic and one that's chiral, instead of asking one molecule to do both. The idea was that this might be more tunable or present, be easier to use or provide sort of, broader scope than we could do with just chiral acids on their own. And indeed, our group has done this in a variety of contexts over the past 2 decades. So here's some examples, primarily activating N-centered electrophiles, which again are not very difficult to activate with acids because they're quite basic. More recently, our group has been exploring the applications of this towards weakly basic compounds, such as cyclic ethers, so oxetanes, aldehydes, and finally alkenes, which are one of the most challenging electrophiles to activate via protonation. And so I want to briefly talk to you about each of these 2 stories today. And I'll start with this reaction here. So this is the Prinz reaction, the cyclization of a tethered alkenylaldehyde. And Dennis Buteladze, who's in the audience here, made the terrific discovery that this catalyst here, a dual hydrogen bond donor, catalyzes this reaction with really, really high selectivity for a ton of substrates. So this is a terrific reaction. This is just a few of the many substrates that work. And you can see that there's a really broad substrate scope here. A lot of different compounds work. But what was perhaps even more striking to our group was the immense rate acceleration that this catalyst could produce. So the background reaction with only HCl is shown in blue. And so this is with 30 mol% HCl. But in this experiment, addition of only 2 mol% of this catalyst resulted in an almost 100-fold increase in rate. And so this is, for organocatalysis, this is a really big increase. This is much larger than we're used to seeing. And so this really made us sit up straight. And we envisioned that studying this process in more depth would teach us something about how this co-catalysis operated. We might be able to extend to other systems. And our initial hypothesis was that, well, it takes a strong acid to do this sort of chemistry. So maybe the hydrogen bond donor binds to HCl and makes it an even stronger acid, which makes it faster. And that's a very common sense way to think. So stronger acids often make things faster. That's why we use them. But we wanted to probe this experimentally. And so we designed the following indicator. So diferrocenyl ketone here, which has a similar pKa to HCl in trifluorotoluene. And so it's a sort of nice ferrocene yellow color when it's neutral. But when protonated by a strong acid, it turns this brilliant blue color here with a striking absorbance at 598. And so we figured we could use this to probe the degree of protonation and see how it changed as we added different catalysts to study the change in the pKa of HCl. And when we actually did this, so with HCl alone at the concentrations employed here, we get about 0.6% protonation. And when we add Schreiner's urea, a known very strong hydrogen bond donor, indeed, we see more ionization corresponding to more protonation, meaning that this hydrogen bond donor in red is making the acid more acidic, like we anticipated. Yet to our surprise, when we repeated this experiment with the actual catalyst for the reaction, shown in blue, we see the opposite effect. So protonation virtually disappears, indicating that the catalyst both makes the reaction 100 times faster and is also at least a pKa unit and a half less acidic. So there's sort of this paradox here. How can a less acidic acid be a better catalyst? And so I'm going to cut out most of this project and just skip to the part here where we sort of figured out the mechanism. So we realized that the catalyst was undergoing protonation by hydrogen chloride to form this Bronsted acidic species in situ, which binds the substrate, undergoes reversible protonation, rate-limiting cyclization, and then can either undergo elimination or chloride trapping to give either of these 2 products here. Only elimination regenerates HCl, which complicates kinetics, but it's fine. And so we, did KIEs, kinetics, a lot of ground state measurements to get this. And so this sort of let us figure out what was going on, but didn't quite answer our key question yet of how does a less acidic catalyst make this reaction faster? And so we turned to simulation, so density functional theory, and also some couple cluster single points. And so we were able to get structures for the major transition state shown here, the minor transition state predicted to be higher in energy, and the background reaction predicted to be still higher in energy, which both, replicates the correct sense and approximate enantioselectivity, and also sort of correctly shows the background process to be much, much slower. So at a high level, we were pretty happy with how this reproduced our experimental results. And sort of furthermore, we modeled a few different substrates just to make sure that our model had some degree of generality. So this is the substrate we modeled first, and we see a pretty good match between the EEs. This is actually a very good match, probably too good. It's likely a little coincidence. But we see for other substrates, again, about the right ordering, giving us some confidence in this model. It also predicts the KIEs correctly. So when we dig into this, here I've omitted the hydrogen bond donor, just to make this easier to see. It took us a few months, but we eventually realized that there's a big difference between the major transition state and the other two transition states. So the major one features chloride beneath the alkene in this visualization, whereas the minor transition state shows chloride on the same face as the oxocarbenium electrophile, as does the background transition state. And another data point here is that the major transition state is substantially earlier, indicating that the alkene is more reactive. It's a better nucleophile. And so this got us to thinking eventually about electric fields. So Arya Warshel, the 2013 Nobel laureate in chemistry, has done a lot of works proposing essentially an electrostatic basis for enzyme catalysis, arguing that the predominant way, not the only way, but the overwhelming majority of enzymatic rate acceleration comes from electrostatic effects, so proper positioning of charges to stabilize the transition state. And although this was initially controversial, there's been some recent work, particularly from Stephen Boxer, probing this experimentally, and essentially showing that the active site electric field correlates very, very well with the barrier to the reaction. So a stronger electric field leads to a lower barrier and a faster reaction. This is ketosteroid isomerase, but there's studies like this for other proteins as well. And so what we essentially believe is happening here is that the different positions of chloride between the two different structures lead to different electric field gradients for the direction of electron flow. So in this case, chloride is beneath the alkene, repelling the electrons here and pushing them towards the electrophile. So essentially, they're flowing downhill, down the field gradient. Where in the other cases, chloride is positioned near the oxocarbenium ion, thus inhibiting the flow of electrons towards the electrophile. And you can actually quantify this, so we can plot the electric field along the forming bond axis. And you can see that in one case it's positive, and the other two cases it's negative, indicating that this effect actually is different in these two cases. And that it's sort of more negative in the slowest background transition state. And so this provides sort of an interesting complement to work that's been done on anion-induced alkene activation. So there's been some good work showing that in sort of cases that proceed through an ADE3 mechanism, where you have the nucleophile attacking just as an electrophile attacks, that the alkene can actually be substantially activated by this process. But this is limited to sort of substrate activation. This isn't very amenable to catalysis because you incorporate the anion into the product. Whereas in this case, at least in this elementary step, the chloride is a spectator. And so it's able to do this in a catalytic fashion. And so this resolves our quandary of how a less acidic acid makes this reaction so much faster, because this is actually proceeding through dual activation. So although the electrophile is activated by H+, and it's less, the concentration is indeed lower for a weaker acid, there's another, the nucleophilic component is activated by chloride, and that the catalyst brings these two pieces together in a way that only aligns with the major transition state. So it's a machine that puts H+ and Cl- in exactly the right configurations to stabilize the major transition state and not the minor transition state. And that's where this sort of unique rate acceleration comes from. And we don't only think that this is operative in sort of this system. So we're thinking about this in a variety of other systems. And one example that I think is particularly striking was in geranyl pyrophosphate C6-methyltransferase, so an enzyme that was recently studied that actually uses S-adenosylmethionine to methylate an unactivated alkene group. And the authors of this paper invoke cation pi effects for how this alkene is able to do such a crazy reaction. And while I'm sure that plays some role in the stabilization, I also noticed that there's this glutamate positioned directly behind the alkene, which likely also plays a role in activating this. So we think that this might be not just operative in the prints, but in other systems as well. So changing gears to talk about the second reaction here. So this is an enantioselective Protio-Semipinacol rearrangement. And although semipinnacle rearrangements have been studied in an enantioselective fashion for a little while, typical precedents have used stabilized cyclic polonium cations to activate the double bond. So essentially add X plus like Br2 or I2 or some NIS, something like that. And you form this relatively stabilized sort of cationic species, which then undergoes a 1-2 shift to form a ketone and this ring expanded product with good enantioselectivity. So this was reported. There's a lot of precedent doing this. They're nice papers. More results, so sort of more recently, people have also explored stabilized oxocarbenium cations, like the ones I just talked about, where here we're forming a cation via protonation, but we sort of have an adjacent oxygen to donate a lone pair and stabilize it. So again, this is, the barrier to this process is thought to be reasonable, and you can control it with a sort of exogenous catalyst. But what hasn't been reported thus far is a Protio-Semipinacol rearrangement proceeding through an unstabilized carbocation. And this makes a bit of sense because the barrier to this process is computed to be very, very low, so about 6 kcals. And this corresponds to a half-life of about 6 nanoseconds. And that number might not mean a lot, but that essentially means that for this short-lived of a species to bump into a catalyst, it needs to have about 100 millimolar catalyst. So the catalyst needs to be at very, very high concentrations. And so, it was thought in the group for a while that, this barrier is really, really low. Even if a catalyst could associate, how are you going to control a process this fast? It's probably not possible. And so we were all very surprised when my colleague, Melanie Short, now Blackburn, actually got this reaction to work with really high enantioselectivity. So essentially using a very, very similar system, so a different catalyst, but otherwise HCl and toluene, was able to get this reaction to go with over 90% EE for a variety of substrates. And so this, again, corresponds to a delta G, so the difference in the two transition states of almost 2 kcals per mole for a reaction that only has a 6 kcal per mole barrier at all. So, how is this possible? And so, we can draw the mechanistic possibilities as something like this. So we can imagine this all being concerted, or we can imagine this going stepwise through protonation to form a discrete carbocationic intermediate. And importantly, this is itself planar, as drawn here. So this is not a chiral product. And the chiral information, the enantio determining step looks like it should be the subsequent ring expansion, where you can choose to migrate either of these two methylene groups. And so, we did a variety of experiments, and these experiments for this project were actually all done by Mao, so I don't want to take credit for them. But so what we found was that alkene isomers give different enantioselectivity. So when you start from 2 different alkenes, which ought to give the same carbocation, they give different enantioselectivity values, indicating that a discrete carbocation intermediate reacting through this transition state can't be the sole determiner of the final EE of the product, that there has to be something more going on to explain this result. And furthermore, we were able to do KIUs that point to rate limiting protonation, which is not in itself conclusive, but is another nice data point to have. The protonation is going to be sort of the highest energy transition state, and that the barrier to subsequent ring expansion will be pretty low. And then we were able once again to use calculations to paint a potential energy surface. And so starting from the ternary complex here, which is just 3 kcals per mole above the ground state, we distinguished between protonation to the psi phase of the alkene and to the re phase of the alkene, and found that psi phase protonation was substantially lower in energy, and then predicted to give a carbocation which underwent rapid migration. And I want to just walk through this in a little bit more detail to explain where we think enantioselectivity is coming from in this system. So if we sort of just once again delete the catalyst and zoom in on the carbocation structures, we see that we have the re-phase protonation, which is higher in energy, and psi-phase protonation, which is lower in energy. Importantly, in these two cases, different carbons are pointing up. So the OH bond is pointing up in both cases. And here we have C4 pointing down, and then here we have C3 pointing down. So that importance is different, we believe. And so from protonation, we go downhill to this intermediate, what we call the psi-phase carbocation, which is still bound to the catalyst. And this intermediate, we think, is predicted to have a very, very short half-life by the computations. So about 19 picoseconds at 4 degrees Celsius. And that number is faster than the barrier to CC single bond rotation. So this is essentially frozen in a given conformation. and is definitely stuck in the hydrogen bond donor's pocket. So it cannot diffuse away and it can't really rotate. So it's stuck like this. And then it can undergo either anti-periplanar migration, so moving the bottom C4 carbon, or it can move the top C3 carbon in what we call a pseudo-gauche migration. And the anti-periplanar migration is vastly favored, is much, much lower in energy. And we think this is due to stereoelectronic factors. So we sort of have this hydrogen bond donor, Lewis basic amide, that's anchored here, and that the orbital alignment is better when we migrate the bottom bond and then sort of push electrons down onto the top of this. And so that's sort of, we think that from this confirmation, this is why anti-periplanar migration is so favored. And although, we're not able to actually see the corresponding carbocation structures for the reef-based protonation because they're not stable in silico, which is not uncommon with carbocations. What we sort of think is happening here is that the protonation step actually discriminates between these two compounds. And so it can be thought of as largely enantiodetermining because the subsequent steps are so fast that the molecule is locked in its conformation and the chiral information is transmitted even through formally planar compounds that aren't planar on very fast scales. So we're very interested in this. Don't think that this has quite been articulated in the literature before as a cause of enantioselectivity. And this paper's in review, so we'll see what happens. But so just one last short story here before I take time for Q&A is about the structure of ethereal hydrogen chloride, which is a commonly used laboratory source of HCl. Is what we've used in the previous projects by and large. So you can dissolve HCl gas in diethyl ether, and it's cheap, it works well, it's stable. And unfortunately, as we started to do all these mechanistic studies, we got really curious about what the solution structure was. Is it monomeric? Is it dimeric in HCl? Does it stick together? What happens? Because this had some minor implications for the kinetics we were doing and seemed like it might be relevant. And so we sort of started to think about different possibilities. So we can imagine that HCl simply just sticks to ether. We can imagine that there's actually proton transfer and we sort of have this tight ion pair where there's an OH to Cl bond. Or we could imagine sort of complete proton transfer with no subsequent hydrogen bond with chloride, that we sort of have an ion paired oxonium species as shown here. And to our surprise, when we dug through the literature trying to find the answer to this, we couldn't really find much. So there's a variety of data, but they're contradictory. They seem like it depends a lot on the exact conditions, and there's no real consensus. Some papers even explicitly say, we're not going to worry about this. It seems too complicated. So we decided to tackle this via in situ IR spectroscopy using both HCl and deuterium chloride so that we could tune the vibrational frequencies and see what peaks corresponded to what. And so when we actually just take ethereal hydrogen or deuterium chloride in ether and dilute it in toluene to mimic our reaction conditions, what we see is this broad peak of 1450 that only appears in the DCl spectrum and not in the HCl spectrum. So this means that this corresponds to a deuterium containing peak specifically. That's obviously because it's not there in the HCl spectrum. And so there's only 3 things in this reaction medium. So we looked at a lot of different possibilities computationally. A few of the more relevant ones are shown here. So DCl itself has a stretching frequency that's too low. And complexing DCl to different things only redshifts. So it only lowers the stretching frequency. It doesn't raise it. And so given that what we were seeing was about 400 inverse centimeters blue shifted from DCl, we eventually realized that this couldn't correspond to a DCl stretching frequency, that the reduced mass was too high. And so eventually the species that seemed most consistent with our experimental data were E and F. So either this sort of just oxonium species or an oxonium complex to toluene. And we reasoned that some sort of like transient combination of these two might reproduce the experimental data well. So we did ab initio molecular dynamics, and we simulated this sort of sphere of molecules with our oxonium ion in the middle for about a nanosecond, and then computed the IR frequencies a few different ways. So this is, again, the experimental data plotted. This is if we take the vibrational density of states by doing like a Fourier transform. Here's if we just take a bunch of single points, optimize them, and then compute the DFT stretching frequencies. And in both cases, we get an ensemble of shifts, which pretty nicely reproduces the experimental IR spectrum. So it's a broad peak at about the right point that looks consistent with the experimental data. Moreover, when we do this in different solvents, so this isn't a function just of toluene. So we do see that the toluene interaction seems to bring it down to lower wave numbers here. But this is true, it seems, of a lot of different interactions. So just diluting it in pure ether gives a similar peak, as does dichloromethane. So we think that this is at least in nonpolar solvents, a somewhat general phenomenon that ethereal HCl actually is not a hydrogen chloride, or it contains substantial quantity of non-hydrogen chloride species. And if we want to think about like actually what this looks like, so this is a representative snapshot of molecular dynamics, showing that indeed, the solvent is nonpolar, so the ions are stuck together, but that there's, this OH is actually free and is bumping into things. And so this is very interesting because we've been using this as a catalyst for a long time. This is a very common reagent that's used. And so it's interesting to think about that if protonated ethers turn out to be such good catalysts, if we've been using them for decades, might we be able to construct more complex protonated ethers and use them as alternate Bronsted acidic catalysts? So, this might be an alternate avenue to construct highly acidic and selective Bronsted acid catalysts that we're interested in exploring further. So that's all the chemistry content I want to tell you about today. So I've talked about how we can screen multiple substrates to find more general conditions. This is nice because we can find better reactions with the catalysts we already have. And again, as high throughput screening becomes easier with robotics and automation, we expect strategies like this only to become more relevant. And then for the second story, I've told you about a few different sort of strong acid mediated reactions, pointing to an interesting role of electric fields, pointing to sort of the strange things that can happen in very, very fast reactions involving reactant intermediates, where even structures that look achiral can retain chirality. And also shown that ethereal hydrogen chloride might not be what it seems to be. And so with that, I want to thank my advisor, Eric, for a great 4 years. Yeah, the freedom and support you've given me has been terrific, and I don't take it for granted. I really appreciate it. It's been a great time. I want to thank my colleagues for screening for Generality. Eugene and I were in the trenches for a long time, and it's glad we finally landed the ship. And Spencer, who's sort of the analytical guru on this. The strong Bronsted acid team, so Dennis, who's in the audience, who took me under his wing when I joined the lab, and also Mel and Raul, for the Semipinacol project. And then collaborators on other projects that I didn't talk about today. So Joe and Mayuko have started bumping in with their really cool story into our screening for Generality story. And so we're excited to be able to collaborate with them and hopefully help them out. Jonathan has worked a lot on pushing forward the strong acid catalyzed chemistry and has a lot of ideas about that. He's a great rotation student. And then I didn't talk about my work with Chuhan at all, but that was on some site selective glycosylation, which I only did computations for, which is a terrific project that merits more space than I have here. Various people for funding like Merck, the NIH, NSF, GRFP, and some internal Harvard funding that we got for the Screening for Generality project. Group members, past and present, and my rotators, and my family, my friends, and you guys for listening. So thanks so much.